How's everybody?
It,
We had a nice little lively pre-class discussion of institutional mission inversion. We will not be doing that today, but it was quite interesting. Uh, any questions business-wise, assignments, anything broken, weird, you're worried about? No. All right. I feel like it's a slightly lighter crew in the audience today. Let's reward those of you who are here and review what we did last time. It's been a whole weekend since we met last. So where were we? And we're supposed to go actually at this point from wherever we were into the moon, which makes no sense at all. So we're going to get back to the moon when we do the Earth. I'm going to talk about light this week and telescopes since they're at the heart of astronomy. But where were we? Yeah. Climate, that's right. What was interesting? Where? Oh yeah, I remember where we left off. But let's go back to the beginning. Yeah.
the beginning,
Well, I don't know. What did we talk about last time?
like basically, like we ended on the different looking at like the charts of the temperature of Earth, like as far back as you know,
Yeah.
and like we're talking about like I know we had talked about how they figure out how cold or like warm things used to be. We were talking about like with the ice cores and like measuring. Was it carbon that they measured?
It was actually an oxygen isotope. Does anybody remember that detail? I know it's a little bit esoteric, but it might be worth remembering because people are always talking about temperatures in the past, and one of your friends might be like, "Hey, how do they know the temperature? You remember? Or do you remember?"
No, I put a note down. I think it was like the CO2 and I was a little bit fluctuated, but I think that's about.
But hold on one second. The oxygen isotopes. Does anybody remember how you get temperature from oxygen isotopes? Tammy? Yeah.
I thought it was CO2.
We talked a lot about CO2 too. There was two molecules we discussed. One was oxygen and one was CO2. I'll just give somebody else a chance. No? No?
I thought
It is extremely technical. Yeah.
some like there's different like there's like different forms of oxygen like on different environments. Like
There's heavier oxygens actually.
yes,
So all the atoms don't seem to weigh exactly the same. And we're not gonna bother getting into that. Yeah.
So basically, simple explanation. If there's if oxygen is, if I remember correctly, if you had heavier oxygen, it was most likely can't remember if it was, I assume it would be colder. Um
It's actually gotta be warmer to evaporate heavy stuff. It kind of makes sense, right?
Yeah. The hotter it is to actually evaporate the heavy stuff, which is then what would
Precipitates out later.
yeah.
So right, so you guys, it's okay that you don't remember the details of that. The point is that it's a really indirect measurement. That's actually we do see these cycles of heavy oxygen deposition in these ice cores that they drill out at the poles, but that's where we're getting this temperature record from. Now the CO2 that you mentioned, CO2 is another piece of this puzzle. So we have temperature, which is swinging wildly on this sort of 100,000 year cycle, and we have these glaciers and everything. And CO2 tracks the temperature too. Now, how do they know the CO2 levels? Anybody? Remember? How do they know the CO2 levels from these? I might have glanced over this too fast. Yeah.
other in life that was alive during that time. Like the size of the life was typically bigger.
I mean, that's certainly a feature of the past. Goosh, we didn't even talk about that. So there were some enormous animals. How do they gauge the CO2 levels, though, from those ice cores?
I think someone already mentioned it.
Yeah, maybe? What would they say?
I was scared of.
Air bubbles. Yeah. So again, air bubbles, CO2 levels, oxygen isotopes, temperature. Yeah.
The other thing I remember was we talked about how CO2 is only 0. Like what was it, 0.042% of the Earth's atmosphere, and so as a greenhouse gas, it probably doesn't have anywhere near as much effect as oxygen does, which is where we tend to measure heat.
Is oxygen a greenhouse gas? I know water is.
Oxygen, yeah, oxygen would be.
I mean, it's a very, very small amount for sure. So, this of course gets super people get really defensive about this too, and I want you guys to be like absolutely clear. Like, I'm not saying that we shouldn't take care of the planet. I'm kind of actually just saying that we can't just blame everything bad that happens on this one little molecule. I think that's really dangerous if we do that, particularly from like following our discussion from before class. It allows the superstructures to sort of invert the mission in a way, right? Because if you can just buy some carbon scrubbers or something, then you're a dirty corporation and you can say, oh, we're clean, we're a green corporation. And it's like, well, what about all that other thousands of chemicals that you're spitting out into the environment, right? That's why I kind of picked on CO2 a little bit. And I love running that test on students every year where I say, how much of the atmosphere is CO2? And everybody always says something out, ranges all the way up to, most of the atmosphere, which makes sense because that's been the messaging over your guys' lifetime. So that's really, really interesting.
I just had a question about like how they actually get like the oxygen and CO2 levels. So I know the CO2 or the CO2 it comes from like the bubbles within the ice. And do they measure the oxygen levels by like do they almost have to like separate the water for like that melt off from the ice into figuring out what actual oxygen isotope?
I think those oxygen isotopes probably come from the bubbles too.
Okay.
They're probably in the gaseous form, if I had to guess.
Remember correctly, that is what they are.
Yeah, but that one's a little bit. So okay, so let me pick on that a little bit. Let me pick on the bubbles a little bit. Like, I think it's good to ask questions about this stuff. So the oxygen isotopes might be a little bit more reliable in some sense on its face because you're comparing the amounts of one oxygen to the other. So it doesn't really matter how much oxygen is inside of this bubble. If it leaked out or whatever, it doesn't really matter. I mean, you can make an argument that the lighter stuff might leak out preferentially, but you're comparing the light to the heavy, right? With the CO2, you're actually gauging the absolute levels. So it's weird to me sometimes because they will show these graphs where the CO2 has, quadrupled in the last 50 years or 100 years or whatever it is. But the way that they're measuring the CO2 on the last data point, or the last few data points, is directly in the atmosphere, right? The way that they're measuring it in the past is in these bubbles. And there's no way to really control that experiment and say that your bubbles are exactly matching the atmosphere or anything like that. So it's a little bit sketchy. Again, I think we should take care of the planet. I just don't know that I don't know that blaming this one little molecule is the way to go about that. Yeah.
I just checked about greenhouse gases. Yeah, for something to be considered a greenhouse gas, it usually has to include oxygen on some level.
Interesting.
So carbon dioxide is one carbon, two oxygen. Nitrogen oxide is one nitrogen, one oxygen. So
interesting.
Yeah, it has to be some form of an oxide usually.
So I think the general principle is it has to be able to, in some sense, the solar radiation has to penetrate the atmosphere through this, whatever gas it is, but then the reflections, right, off of the Earth are often, a lot of light is leaving, a lot of heat is leaving through a wavelength of light called infrared radiation, right? We'll talk about light. We're going to get into that today. But the wavelengths of light kind of determine its properties. And so these greenhouse gases will screen particular wavelengths and trap the heat. That's the idea anyways, that it acts sort of like a transparent lid on a greenhouse that keeps all of the heat in, something like that.
Yep.
Yeah.
Bouncing off the previous question, you were talking about scientists can know like ancient temperatures from ice cores. And I wanted to know if we like knew how to reliable the isotope measurements actually are.
That's what I was trying to say, that I think that the isotopes are at least a relative measure. You're comparing heavy versus light, right? The CO2 measurements from the bubbles are absolute. So they're saying there's this concentration of CO2 inside of this bubble. Therefore, the atmosphere was at this concentration. Was it? I don't know. Maybe. Maybe it's a reasonable assumption. I don't know. But I think that just from first principles, knowing almost nothing about this otherwise, that if you're comparing two things inside of the same bubble, that comparison seems like it will hold no matter what. You're not saying like there was tons of this heavy oxygen. You're just saying there was tons of it relative to the light oxygen. So it's a relative comparison. So it just seems like a more stable pronouncement to me.
So basically, we're kind of like going this data that we know.
Yeah, it's a comparison, right? It's just better science, right? Like let me give you a different example. Like it's really hard. You guys have probably experienced this before. Like you get sick. You go to the doctor. Doctor gives you a medicine, and you get better. Well, did the medicine make you better, or were you going to get better anyways? You have no way to compare because you can't have two of you, and one of you doesn't take the medicine, and one of you does take the medicine. So the hallmark of clinical trials is they try to do these placebo-controlled blinded studies where they really do give the medicine only to half the people. They give like sugar pills to the other half, right? But you can't do that with yourself. And so it's not a very good scientific study to say, well, I took this medicine and it got better, therefore the medicine cured me. You don't know. Maybe you were going to get better anyways. And so in some sort of relative comparison, you're always better off. It's just a more robust scientific approach to understanding what's happening. That's why, but again, this, I don't fault them for trying too, because talking about the deep past is super hard. It's really, really hard. And people do want to make a stories up because it is clear that there was a glacier covering a huge part of the northern hemisphere not that long ago. And it would be really, and it's kind of apparent that it's been happening for a while off and on. So people want to understand it. Yeah, Corey first.
So I wonder if we've actually just tried it and tested more recent bubbles in ice compared to since we've had atmospheric sensors and seen if they're the same.
Yeah, but then do you know if it's leaking still? What's the leak rate?
And we could probably find that out by having a few different eras of
Yeah.
since we've created those detectors.
Yeah.
When we had them, or
That's
how accurate they
That's
were.
exactly what I was going to
Yeah.
say.
Hopefully that is happening. Hopefully. Hold on one sec. Ezra, you had something in the back there. You have your hand up?
No.
Oh. Well, hello anyways.
No, that's exactly what I was going to say. Is that it's actually because I looked into the ice core thing over the weekend, and yeah, they're trying to get a comparative thing where to get current bubbles that match up to see if those match up with the more detailed, like direct CO2 level readings we have with atmospheric breathers, basically. Uh, and so far they're kind of close,
Yeah.
but they don't know, like they've done, but none. I didn't.
Yeah. But if you wait 1,000 years or whatever, yeah.
Clue about the leakage or any of that.
Yeah. Yeah. It's tricky. It's tricky. So, I mean, look, at the end of the day, it's pretty obvious that I may as well just throw this slide up that we ended on last time if I can get back to it. This kind of thing is what the ice cores tell us over time, which is pretty weird, actually. Yeah.
How deep do they usually drill into the ice?
Oh, I don't know the answer to that.
10,000.
No idea. Yeah, somebody want to Google that or ask some robot the answer? That's a good question. Maybe you can look it up. Do you have a computer or phone or something?
Some robot. Just look it up on Google.
Yeah.
Ready robot, please.
Well, you gotta make use of the information channels that we. That's a good question. The answer, perhaps the more relevant answer, is that the deposition level is correlated to the years that we see going back. And there's other things that they can correlate to kind of give themselves confidence in the year estimates that they're getting per unit depth, right? Because you can compare things like tree rings even. You can compare carbon dating estimates too for different elements that you find. There's different correlations to make these events line up in some way. And so we have a pretty good picture of what happened for the last, 10 to 50,000 years or so with using other dating methods. And then we see this pattern extended over and over again into the past. So the idea is, well, it's about the same. Yeah.
They range. Shallow ice cores are 100 to 200 meters, but
Whoa.
the deep ones are 3 kilometers.
3 kilometers?
The deepest was 3,769 meters.
That's insane.
And that was
They're getting a bubble out of it, too.
that was a couple
Yeah.
minutes.
That is bananas. All right. Well, there you go.
Ago.
Yeah, so I think we kind of stopped our story off like looking at this thing and how kind of strange it was. And honestly, I think this is actually one of the more beautiful mysteries that's out there in terms of being a huge, huge piece of our history on Earth, that the standard explanations are a little bit unsatisfying. So does anybody have any idea for why people think that this happens? It's okay. So the basic idea is that there's a number of natural cycles in the astronomical landscape, in the celestial motions of the planet. So we talked about how the North Star is in a different place at different times, right? Or sorry, there's different North Stars at different times. So, when the ancient Egyptians were building the pyramids, there was a different North Star than there is today. And this is also one of the reasons that astrology is kind of bizarre too, because it's based on star positions that are no longer the star positions because, for whatever reason, the positions of the stars change. The standard explanation for that is that the Earth it is tilted at 23 degrees, but it kind of wobbles a little bit as it does that. So we talked about how in seasons, because the Earth is tilted, it's making its way around the sun in such a way that it's always leaning toward or against, into or away from the sun, right? So you have winter and you have summer, depending, for both folks on the northern and southern side of the hemisphere. But there's this other element, which is called precession, which has to do with the theorized way in which the top of the Earth wobbles a little bit. So this is about a 23,000 year cycle overall that this wobble is supposed to happen. There's also changes in the eccentricity of Earth. So that's the ellipticalness of it. There's more or less, I have a hard time saying this word. I don't even know if it's the word. There's more or less eccentricity depending on I was going to say elliptivity, but there's more or less eccentricity. So the orbit of the Earth actually changes in how flat, like how elongated the elliptical orbit is. And that's on about 100,000 year cycle. And the actual tilt of the Earth, the 23 degree tilt that we have, actually changes and lessens on a cycle of about 40,000 years. And so there was this Serbian geologist named Milankovic who proposed an idea. I wonder what year that was. I don't actually have it written down. It was in modern times. Proposed essentially that some amalgamation of all of these different forcing regimes would create a situation where the temperature would swing in such a way that the ice caps would, well, let's say the temperature would get colder, the ice caps would come, and then they would start reflecting. As they grew, they would reflect the light, and you would get this feedback loop where you actually got full-on glaciation cycles. And then, once again, as they started to melt, the same thing would happen, and you would have a feedback loop in the other direction. That's pretty much the standard explanation for how this all goes down right now. The problem is that this happens on an almost clockwork 100,000 year cycle, except the only element that I just told you about, which has a 100,000 year cycle, is the eccentricity. And the eccentricity can only account for about 0.1% of the temperature swings that we see. And so this is really the only explanation that's ever been entertained in terms of seriously being able to explain why in the world this happens, but it's a pretty rocky explanation on its face. And I think that most people would agree that there's probably more to this story than meets the eye. Now, I pointed out to you guys another little fun piece of this mystery too. I don't know the answer to any of this stuff, so I'm just kind of throwing this in your lap. It's really, really cool. But this is what happens when the Earth gets cold every year, right? And gets warm. The ice sheet grows from the North Pole, right? It's the furthest place from the sun on average. The poles are always going to be furthest away from the sun on average over the course of a year, right? But that's not what happens during the glaciations, or at least during the last one. During the last glaciation, the ice sheet was centered over Greenland, which is really wacky. So I personally think this story is far, far from complete. I think there's something much more interesting at play. Yeah, let's go Isaac first.
Could that be attributed to like the precession and the tilt? Because then like it would almost make something a little different, right?
It's supposed to be the precession. It could. It's too much though. Is the problem? It's too much. Yeah.
I think it might be a result of either a combination of like the ocean's like heat currents, because those also affect where the ice sheets are in our season, so that might also affect it, and it could also be a effect of, you know, the core, the internal temperature of the Earth's core and where that heat is transferring.
Yeah,
Does it like the convection cycles of the Earth's?
I think you're right. That more likely than not, there's a very subtle explanation that has to do with the, let's say, heat balance of the planet and the storage, places where like the ocean currents are changing, something like that. That's quite interesting. But it is pretty bizarre, and it does appear that during the last ice age, let's call it an ice age, even though that's not quite the right term, but during the last glaciation, it was actually quite temperate in Siberia, which is weird. Because again, the whole thing seems to have been centered not directly over the poles like it does the rest of the time. I would think that if it, I don't know, it's very strange. If there is an ocean current explanation, I would think that that would hold year to year as well, but it doesn't seem to. There was a really fun book, though. I will tell you guys about this. There was, and the only reason, yeah, well, there's a really fun book. Gosh, the name is escaping me. It's written by Charles Hapgood in the 1950s. And the foreword is actually written by Albert Einstein, too. So this is a wacky idea. But, at least Einstein endorsed it enough to write the foreword for it. So it couldn't have been that wacky at the time. But Hapgood was proposing this idea, and he had a whole sea of evidence for this. It's actually a very beautifully written book. But his idea was that the crust of the Earth sits on a somewhat viscous asthenosphere, which is kind of like a liquid layer underneath it. And he figured what was going on was that the ice would build up at the poles, much like it does in the standard explanation, and it would kick off this feedback loop. Again, it would start to build up really fast as the ice reflected more and more, the sunlight got colder. But at some point, there would be so much mass tied up in the pole that it would actually, as the Earth was spinning, because we talked about, Foucault's pendulum and the spinning of the Earth, that it would actually sort of tilt the crust on its viscous layer underneath, and the whole crust would just sort of a little bit like this, which is pretty wacky and far out. But and later, I guess Einstein did some calculations and said that he was unconvinced that this was what had happened. So. Really cool book, though, honestly. Pretty fast read, too. These people really used to know how to write back in the 1950s. So that's a pretty far out idea. I don't know. I have no idea what's going on. I find the Milankovitch cycles to be like slightly underwhelming, though. So there's this other piece. Okay, well, I'm not even going to bring that up. We'll get to that later. Thoughts, questions, concerns? Yeah.
Happens to the poles when that layer shifts? Do they remain? Do they?
In Hapgood's conception?
Yeah.
Yeah. Well, he just thought that the whole crust, like everything,
And every
would just slip on the viscous underlayer, basically, as one unit,
feel like the poles are shifting because that's something that I read in the
The
beginning.
magnetic poles are definitely shifting, yeah.
Like air runways and things have to be slightly tilted. I mean, things
Yeah.
are moved.
The magnetic poles are a little bit different than the axial poles, like the spin poles. Now, they do correlate with one another, but first of all, we've never, as humanity, lived through a magnetic pole reversal. They happen, I don't know, on the million-year order, let's say 700,000 years or something like that. And you can see these nice stripes in magnetizable rocks where the geomagnetic poles have reversed, like clockwork, like I said, every 700,000 years or so. And the pole starts to drift before the reversal. So we're due for one of those. I don't necessarily think there's any cause for alarm about that, because it's not in any way the way that we understand orbits. It's in no way tied into the actual axial orbit. Also, this thing that we were talking about, this cycle happens on a 100,000-year cycle. So it doesn't seem to be correlated to the magnetic pole reversal at all. But yeah, this Hapgood guy was, and some others at the time were genuinely proposing that the crust itself would slip. I always called it crust slip theory, but I know he had a better name for it than that, and I just can't remember it right now. Yeah.
What would like the result of the magnetic pole shifting be? Like, what would is there anything like crazy that would change if something were to happen like that, or is it just like the direction is just different now?
I don't know. I mean, it might confuse some sort of geostationary uh, navigation systems temporarily. It might be a weird day or a weird 100 years. We don't know how long it takes, right? And we don't know anything about it. The last one happened 700,000 years ago or something like that. So yeah,
Well, it does affect mostly like migratory birds, and
yeah,
whatnot, because that's how they navigate.
yeah.
Their migratory system is
They probably figure it out though, you know.
also affects our magnetic compasses, though we stopped using those a while back anyway. Um, but generally, the magnetic poles, most of what they affect seems to just be life on the planet and nothing more.
Yeah,
General.
yeah.
Maybe
Yeah, I'm personally not losing sleep over this.
I haven't seen much of that now, but maybe.
Yeah, yeah. I mean, there's always going to be some apocalyptic cult who's like, the pole reversals, but it's like, I don't know. There's not any real evidence for it being a disaster. This, on the other hand, is pretty crazy. This cycle is definitely real, and it would have crazy consequences. Like we are, as you can see, in one of these warm phases today, right? It's actually it's a little bit cooler than the last time today, but it is warm, right? We're in one of the warm. We call it an interglacial phase of the climate cycle. And if it was to just go into full-on glacial phase tomorrow, it would be quite interesting, I'm sure. Although
I don't think Russia would like it.
it appears to take a while to do it. You know, I think it would be on the order of centuries, if not millennia. I don't think that it would happen overnight. But it was certainly wild for people. If you think about people coming off of this last one, right? So the last glaciation period, the cold stuff, it ended, you know, quite a long time ago, but it started getting warmer over here, right? And that was, maybe 15, 13,000 years ago, something like that, 15,000 years ago. And that must have been pretty wild. I mean, I think the sea levels rose by 300 meters or something over the course of the last 10,000 years. A lot of that probably happened up front because there was ice dams all over the place. And when the ice dams would melt and break, they would let loose all of this mountainous water. And it must have been totally crazy. Very, very floody, a very floody era of human life. I mean, there's this, you guys know about Doggerland? That's always fun. You guys ever hear about Doggerland? You know about Doggerland? Tell them about Doggerland.
What's this area of Europe that is basically all underwater or like has since just been buried by sediment over time. It's like a lot of ancient England is basically buried under the oceans.
Yes.
Yeah, it's basically the whole North Sea area, right?
Yeah.
Pretty crazy. So there's like just people living there where there's just full-on oceans today. And I assume that, I don't know if you guys ever paid attention to this, but people love to live by the ocean, right? That makes me want to tell you guys about the aquatic ape hypothesis, but I'm going to never get to light if I do that. Okay, people love living by the ocean, so God only knows how much history is just completely erased during these, 300 meters. If you go down to the beach today and imagine 300 meters, I mean, fortunately we're in the warm phase, so that's not going to happen probably, but if the ocean went up by 300 meters, like say goodbye to New York City and LA and basically everywhere that people congregate, right? It's right by the ocean for the most part. So that's pretty wild. And yeah, it must have been just a wild change. So that happens. And it's gonna, Gavin Schmidt argued a little bit, but I think it's gonna happen again and again and again and again. This is something real that is consistent. And maybe human beings will have an impact on this one way or the other, but I don't think we're going to be able to stop it. It's a moving train. I don't think you can just jump out in front of it completely. Yeah.
Well, the fear is that because this has started since the beginning of the current ice age, which is just whenever there's been any snow or ice on the poles.
Right.
Before the last, before this current ice age started, and there was no, ice on the poles, the Earth was significantly hotter.
Right. That's a really good point. So this word ice age gets abused all the time.
Like if we melt all the ice on the poles, it will end up in a runoff, and the whole world will get super hot.
It'll be a jungle.
Melted. And,
Yeah.
But then you look at this, and you're like, well, actually, we're not even close to the point of previous interglacial period, and
No.
didn't melt the ice.
No.
So,
No. I mean, I'm sure humans can mess things up if we're not careful. I
mostly like oil pollution.
Yeah, I have a tendency. We would more likely kill ourselves off, is what I'm more afraid of than us harming the planet in the long run. I think it could probably get along just fine without us, but that's not an outcome I'd like to see happen. So,
Maybe our hubris.
what's that?
Maybe our hubris.
Well, we can beat that, hopefully. All right, goodness gracious, where have we ended up with all of this? All right, so we have this insane cycle. It's happening. The explanations are scant and obscure. We have Milankovitch cycles, which are kind of a amalgamation of other cycles, which are, range between measured and theoretical. It's a very hard thing to explain from where I'm sitting, but I'm not a climate expert or anything. I just thought I would take a minute to point out that this is a really cool mystery. And there's lots of cool mysteries out there that need attention. So something to think about. Any final thoughts on that before we go on? No, what's that?
Light.
Light. Okay, let's do light. And honestly, I think we're gonna. I'm fine with spending the whole week doing light if we have to, because it's so important. It's light is at the heart of almost everything that we've already been talking about, because we are extraordinarily dependent on visual information for comprehension of our environment. I mean, humans have incredible eyesight. Do you guys realize how good our eyesight is? It's unbelievable. We have some of the best eyesight of any animals on the planet.
Shrimps.
It is unbelievable. Shrimps have good eyesight?
Not as good as a mantis shrimp.
Ah.
See like 16 different color cones. They get to see colors we could never comprehend.
That's really funny. I mean, we're way better than any other primate, and much better than most other mammals. We just have incredible vision, and in all honesty, it's kind of the way that we think too. I like to point that out here. It's like, what do you say if someone's smart? You're like, that person's bright, right? Or like, what else would you say? You're like, someone's like, do you see what I'm saying? Like, what the heck does that mean? How can I see what you're saying? Like, but it's the way that our brains interpret information. Like, you close your eyes, you see solutions to problems, you have vision about the future. Like, all of the words that we use for comprehension and clarity and understanding and intellect.
Sight or sound.
What's that?
It's either sight or sound, actually.
It's almost always sight. That's what I'm trying to impress upon you. It's like, we are so dependent on vision. Like, that is what human beings do. And we think in terms of vision. We visualize solutions to problems. Like, if you start paying attention to the language you use to describe eureka moments, and you will notice that it's all based around vision. So light is really, really important to us. The problem is, what is light, really? That's the problem. And if we can't answer that question sufficiently, then how can we say what the light means that we're using to make sense of everything from the stars to the planets that we're going to be talking about today, to the asteroids, to the comets, to the other side of the galaxy, like we were talking about in the first week? So we need to make sense of light itself, because a huge piece of astronomy, more so next semester than this semester, especially when we start looking at stars and really distant stuff, comes down to examining their spectra, right? If we want to go looking for life on other planets that are light years away, how do we figure that out? Well, we have to see what molecules are in the air. And how do we do that? Well, we have to look at the spectra. So we need to talk about spectra this week. And then we obviously need to talk about telescopes too, because that's at the core of where all this data is being generated. But I really, really want to take our time and see if we can't get a grasp of what light might be. Now, we have brilliant equations for light, and I'm going to go through some of the things that we know about light, but there is no generalized consensus for what is happening on a material basis between two atoms when light happens, right? So that will all come into focus in a second here. So for most of human history, people split hairs about light. What did they think? Well, people, and the ancients, especially I'm just talking about the West, so ancient Greece, was often presumed that you shot little bowling balls out of your eyes, and those gave you the sensation of light by somehow bouncing off of the objects in front of you, which isn't too crazy because you really do, it turns out, end up seeing by virtue of reflections and so forth. But we've kind of abandoned the idea that you shoot light out of your eyeballs. There was, of course, a Dark Ages, and then this debate was resurrected. Now, we talked a little bit about the ether before. Didn't we? Did we talk about it?
Ether, yeah.
We talked a little bit about the ether before. So, for most of human history, for most of the history of rational inquiry, people what we would call physics today, trying to make sense of mechanics, right? People assumed that there was some sort of fluid stuff or a gaseous, misty thing that was in between all of us and in between us and the sun, and somehow mediated the force of gravity, and it also mediated the light signals that were going on. That was kind of a foregone conclusion. The Enlightenment philosophers, when Newton came along, we talked about Newton. He was very important in this whole gravitation discussion. He added the mass quality to Kepler's relationship. Newton tried to resurrect kind of the older idea that there was little he called them little corpuscles, but he thought light was this really lightweight, what a horrible word to use, but a very almost massless particle of something that was shot around, right? And why did he think that? Well, because he noticed that light seemed to travel in rays, right? And so do bullets and rocks and things like that, I guess, if they're going with sufficient speed. So it wasn't a completely crazy idea. On the other hand, there was, Newton's arch nemesis, René Descartes, who was arguing that no, the ether itself could deform in such a way that some continuum in the background could have vibrations in it, which might be the cause of light. Yeah.
Newton's arch nemesis was absolutely Lorentz.
Lorentz?
Because they had it's basically what probably killed Newton in the sense that they argued over who actually invented calculus.
Are you thinking of Leibniz?
Leibniz.
Leibniz, yeah. There was two Lorenzes later. They both get confused for one another, and they were 20th century scientists, I think, if I'm not mistaken. But yes, you're right. Leibniz. That's really a crazy story too. Well, Descartes, from a philosophical perspective, was very different from Newton in many ways. But in the sense of the mediator of light and gravity, Descartes imagined that there was this homogeneous substance everywhere. You couldn't see it, but whatever was happening to this substance informed whether there was atoms there, whether they gravitated to each other. There was vortexes in this ether stuff that caused gravity. He had this kind of continuum mechanics idea about the nature of the ether. Newton really tried to stay away from the ether. I think he in some sense imagined that there must be something like that there to make sense of gravity, but he didn't really want to write about it or talk about it or think about
He
it.
did put in his Principia Aether, and the idea that Aether flowed continuously down toward the Earth and the Sun, and light as particles flowed through it.
He had like a particle version of it, right?
And the way they traveled through that Aether caused the wave nature of light, in that we were just seeing the of it through a medium like water. So he was thinking of light like think of shooting a bullet through water or air. That's how he was trying to think of it. And then he thought of it. And after another book after Principia, it's like, I think probably doesn't exist.
Yeah, he went one step further and he was like, it's not our problem, actually.
Yeah.
So yeah, you mentioned the wave theorists. So the wave theorists were kind of a thorn in the corpusculus side. So there was always this argument about whether light was these little bowling ball thingies or whether it had a wave-like nature to it, right? So turns out to be true, that it's actually, this is a very real aspect of light. Light exhibits this kind of transverse wave property. So that word transverse is going to come up over and over again. I want to be totally clear about it. So the frog is over here, and he's making transverse waves on the surface of the pond. Transverse waves just can be thought of as they're oscillating, not in the direction of their propagation. They're oscillating in a different direction, right? In this case with the water, the surface of the water is going up and down, but the propagating wave is actually moving outward, right? So this is very similar actually to light. What is oscillating we'll have to get back to, because obviously what's oscillating with the frog in the pond is the level of the water in the pond. It's not quite so simple with light. So yeah, a bunch of folks showed up after Newton and started to argue about the wave nature of light. Newton kind of realized that light was separated into these different colors, but it took a number of people really working on the interference question to say that, to really mount an argument that light was some sort of wave. Wave of what? I don't know. Nobody really knew at the time. But they did know. This is actually Thomas Young's experiment. He's one of my favorite super bosses from science history. He worked on everything from the Rosetta Stone to music theory. Just a crazy dude. I think he was a physician by training as well. But he did this slit experiment where he basically would poke these little holes and notice that as light went through the little holes, it would actually create interference patterns on the background. So some of the light would cancel other pieces of the light out, right? So you'd get these banding structures where there would be intensity of light and then darkness and then light, darkness. And so there was some sort of interference happening. That's really strange because it doesn't make sense for light to be little bowling ball corpuscles in the Newtonian sense and to interfere with one another in this way. So the wave people essentially ended up winning out. So I want to make sure that we understand what people do understand today. This, in some sense, the wave system proved to be true. Light is absolutely a wave. A wave of what? Well, through a bunch of other experimentation and mathematics, people came to understand light as being oscillations in electromagnetism. That's a weird thing to say, though, because what does it mean exactly that you have oscillations in electromagnetism? What it means is, this guy, Hertz, does this experiment where he oscillates the electricity in a circuit. And he's able to transmit, by doing that, he's able to actually cause a little loop of wire on the other side of the room to spark. And he builds out, this whole theory that this electromagnetism, this electricity is actually being transmitted to the other side of the room by these oscillations. And the oscillations, by the way, in the case of Hertz's experiments, were really, really, really long waves. They were radio waves, actually. So when I'm talking about light, I should have said this at the beginning of class. When I say light, I mean the entire electromagnetic spectrum. So everything from tiny little high energy X-rays all the way up to the huge, radio waves as big as this classroom, right? These are all, in my book, forms of light. Yeah.
Microwaves cook your food with light.
Yeah, microwave ovens. They cook your food with long wave.
Mesh in front of the window.
Yeah.
As if the holes are just small enough and thus the mesh big enough to break the microwave so it doesn't boil your blood.
It is absolutely true. Yeah, and so in general, I think that we can think about, we can think about this on a whole spectrum. I've drawn it out here. My point to you is that, through most of the history, even when people were doing these wave interference experiments in the 1800s, they understood that light was a wave of something, but they didn't know what is waving, right? This Hertz guy comes along and he's like, there is some sort of electromagnetic signal that is waving. And it comes down to the polarity, the flipping of polarity, like an AC circuit that's being transmitted across the room in Hertz's experiment. So that's weird. So, Maxwell develops this idea that it's this standing, this self-propagating electromagnetic wave. But what in the heck does that mean? What does it really mean? And I think that in some sense, Hertz's idea was closest to the truth, which is that somehow oscillating an electromagnetic system, a circuit, positive to negative, negative to positive, driving the current back and forth, back and forth, back and forth, that somehow is capable of exciting other atoms at the other side of the room into the same state of motion. And that's fundamentally what an electromagnetic wave is, right? So, okay, so we can accept that there's some sort of electromagnetic oscillation at the heart of all of this. We don't quite have a picture for how the atoms are doing that yet. We also know light goes in a straight line, which is pretty bizarre. There's some sort of ray-like nature to it. And then we increasingly have this picture that atoms must be responsible for this. Somehow the matter is itself responsible for generating these light signals. So you guys seen this, you probably saw this in chemistry, right? You have this idea of how an atom makes a photon, right? Makes a wave of light, right? You've probably seen something like this. The basic idea is you have the electron, it's in some orbital around the nucleus, and it goes into a higher energy state, and then it relaxes, and when it relaxes, it emits a photon. And we can just think of a photon as a whole wave of light right now, right? So that's an interesting picture. The problem is that atoms aren't really like this, right? When you can actually study atoms, and we talked a little bit about the shape of atoms when we were talking about gravity. And the way that we actually model atoms has to do with the way that their outer surface, the electron, takes its shape when it's driven in certain ways. So these are, in some sense, different orbitals that you can imagine for an atom to have. Its electron can take different shapes. So what's it mean when the atom gets excited and its electron jumps into a new orbital? Well, it just means that the outer surface is excited into a new shape, essentially. It's got a new vibration to it. Now, what's really cool, this is a simplification because the reality of the situation is that atoms are essentially spherical. Those shapes that I just showed you have to do with the kind of vibratory waves that can be found in the polarity of the surface. Hang on to that for a second. It sounds complicated. It's not that big of a deal. Basically, the outer surface of the atom has a particular vibration to it. When it gets excited and goes into a new energy state, it has a new vibration to it. Have you guys ever seen these experiments where people put sand on a plate and put a speaker underneath them before? Pretty cool, right? So what's happening? Yeah. Yeah, it's reacting exactly to the wavelengths. In some sense, the sand is getting driven out of it's getting moved around by the presence of this sound wave, which is literally a physical vibration happening underneath it. But there's places where it's crashing into itself, and depending on the frequency in which it's crashing into itself, there's going to be null points, little places where it's easier for it to just stay put as the whole platform is vibrating. The result is you get these super beautiful harmonic patterns that result from it, right? So the atom is something like this, actually. This is what we can think of, is that the surface of the atom, the electron shell, is also driven into higher and higher degrees, right? There's some sort of drive impulse, like the tone that's being played on the speaker. There's something like that, which drives the surface of the atom into different deformations, right? That gives the atom its shape, actually, which is really fascinating. Now, what is it that drives the atom into new states of motion? That's the next logical question. What is the source, in this analogy, this is called a Chladni plate, by the way. So in the Chladni plate analogy, you have a speaker that's playing tones. Well, what's the equivalent of that for atoms is the next logical question. What is driving the atoms into increasing degrees of excitement? Well, if you go back to the Bohr model of the atom, the high school textbook chemistry model of the atom. The electron is going into a new degree of excitement, right? It's getting charged up, right? So this concept of charge, you guys have heard of like positive and negative charge. What the heck is positive and negative charge? It's a really nebulous, weird concept, actually. It's just, electrons are negatively charged, protons are positively charged. What the heck does that mean? Well, if the electron is the outer surface of the atom and it's getting charged up, what it really means is that it's getting driven into a new state of motion. It's getting extra drive added to it from another atom, presumably. How can that happen? Well, it could happen through contact. You might have one buzzing, vibrating atom that touches another one and transfers the charge that way. Or you might be able to do it at a distance with light, which is really, really interesting. So one of the ways that I like to think about this, I'm going to come back to Carver in a second. One of the ways I like to think about it is with the antenna. So this is kind of the most well-defined way that we could study light, in my opinion, is through an antenna. We're all using antennas. We've got cell phones, right, that have antennas in them. And so we know the cell phone signal, this, whatever I'm getting in here, is 5G or whatever, is a light. It's a band of light waves. There's some frequency space that you can access with the antenna here. What determines what my cell phone picks up? Like, my cell phone's not picking up X-rays and gamma rays and stuff, right? Because its antenna has been tuned, not only the length and the size of it, but it's also tuned in terms of how it oscillates its own electromagnetic polarity inside of it. So inside of the antenna, you're amplifying certain wavelengths by changing the positive end of the antenna to the negative end of the antenna as fast as you wish to in order to correspond it to the wavelengths that you wish to receive in the antenna. Likewise, over at those towers, wherever these cell phone signals are emanating from, over at the tower, or I guess when you connect to a tower to talk to somebody and transmit, you're doing the same thing. You're oscillating your antenna at a characteristic frequency that corresponds to the wavelength of light that you want to put out into the world, right? So these antennas are actually little light generators, and they're tunable, which makes it really easy to start to understand what's going on with light, because the atoms are clearly doing this dance where they're going from being overcharged to being undercharged. And I want to come back to this and play with this idea of charge a little bit more, because charge is at the heart of all of this. But they're going from being overcharged, negative, to being undercharged, positive. And it's oscillating. The whole length of the antenna is doing this. And the result is that it is putting that same information about its oscillatory state out into its environment, and it's affecting the things around it. And through some act of relay, that's ending up at an antenna at the other end of the picture. So this is I think, a more accurate picture of light, but it's a little bit different than the one that you find in most introductory books, because most introductory books still kind of default to the Newtonian light is a sort of ball of energy thingy that gets shot off into space and goes and does magic, right? That's kind of the way that this Bohr model treats light to some extent, right? The thing gets excited, the electron goes into the new orbital, and then it relaxes and it shoots off this magic light photon thingy. But I think that the antenna is actually a probably safer way to understand what's actually happening. One second, let me ask you one last question, and then I want to take questions and make sure we're all on the same page here. Can you have light in a single atom universe? I don't think so. What do you think, Ezra?
So I mean, are you saying like the universe with only one atom?
Yeah, if the universe only had one atom, could there be light? Because kind of everything that I've been pointing out today, in some sense, is all about the interactions between an emitter and an absorber. Your antenna, right? You got to call somebody at the other end of this phone, or you got to receive a call. I think that the entire concept of light makes very little sense without considering two atoms. The tragic part is that in almost all of our electromagnetic theory, we don't consider two atoms in the transaction itself. So, I wanted to mention this dude he's actually brought up. He made his career actually in semiconductor physics. He's a Caltech professor that I got really close to over the last few years, and he's championed this idea that the best way to understand light is to understand it as a dissipation of vibratory motion, this thing I'm calling charge ultimately, from one atom to another. Somebody's excited and somebody is underexcited, these two atoms, and you dissipate that motion into the partner atom. In other words, light always involves a transaction of energy. You could think about it that way, but I would just say of vibratory motion from one atom to a next. And he actually pointed out this quote. This is a really old quote from the 1920s from G.N. Lewis, who's one of the fathers of electron chemistry. And G.N. Lewis just rattles this off in a lecture at the Royal Society, I believe. And he says, I'm going to make the contrary assumption that an atom never emits light except to another atom. I propose to eliminate the idea of mere emission of light and substitute the idea of transmission, or a process of exchange of energy between two definite atoms. Both atoms must play coordinate and symmetrical parts in the exchange. That is actually a really radical idea that you won't find persisting in most books on optics today, most books on electromagnetism. We tend to just isolate a single atom and talk about, the changes that happen in that single atom. It's almost never discussed as a pairing. So this is something I think that's really important. I think we have to really start thinking about light as an actual interaction between atoms as opposed to this kind of magical thing that's going on. That gets us into a space where it's almost always a network effect of relay, right? When you guys are looking at me right now, you're not just seeing the light bouncing straight off of my face to your eyeballs. It's actually relayed through gazillions of neutral atoms in this room right now. I don't think that it's just magically going through them. I think they're preserving the momentum of that transaction one to one to one to one all the way back to your face. And I think there's evidence for this, particularly the way that light behaves inside of media, right? So if you guys go fishing, you'll see light kind of seems to get bent inside of media sometimes, right? Inside of water, stuff like that. And this refractive ability, in some sense, can be explained by each one of you break up the water and treat it almost like a lattice. And the lattice is a bunch of antennas, basically. And the lattice has charged elements itself, and they'll actually interfere. They'll set up their own standing waves as they get excited by the light. And they'll interfere to such a degree that the light almost appears to slow down inside of these media. And this causes it to divert downward. But it's not really slowing down. It's just the effect of these transactions that are happening inside of that lattice over and over. There's millions of antennas. You really got to start thinking of each atom as an antenna. So, okay, let's take questions about this. Let's try to make sense of this.
This guy?
This is Carver Mead. Sorry, that's his book.
Okay.
It's a fantastic little book. Chapter 5 is easy for you guys to read if you're interested. But he basically, takes standard quantum electrodynamics and relates it to this transactional concept that you can treat atoms as little resonators. Of course, the thing that is resonating is not the surface of the pond. It's not a physical displacement that's resonating. It's actually the positive or negativeness of the atom, which can really only be understood as how overdriven its surface is, as far as I'm concerned. But those words positive and negative charge are often completely left undefined in almost every single scientific context that I've come across. Yeah.
Two things.
Yeah.
So
let's go.
You brought up earlier negative equals overcharged?
Yeah, it usually means an excess of electrons.
Excess, okay.
But yeah. But assuming that electron just kind of means, again, I'm interpreting this the way that makes the most sense to me. But assuming that electrons aren't little bowling balls, assuming they're actually the state of motion of the outside of the atom, which I think is a bit more rational than these magic thingies that can just fly around. There's many reasons to believe that electrons aren't little bowling balls. So if we look at the speed of electricity inside of a wire, it's really, really fast, actually. But if we try to model how fast an actual electron could move from one atom to the next if they're little bowling balls that have negative charge, it's really slow, actually. It's like orders of magnitude slower than the speed of electricity. And so people have wrestled with that over the years. It's been resurrected as an argument recently on the interwebs. There's been a bunch of famous YouTube videos about this. It's very, very, very hard to explain something as simple as electricity with the flow of little magical electron particles. And so I'm personally I'm not too interested in treating electrons as little bowling balls that get moved around. I'm more seeing it as the state of motion of the outer surface of the atom, which I think is a bit more sane. I also think it's just more congruent and less paradoxical. So where else can we see something like that? Well, we've seen this kind of thing before. So you guys know that heat, until, I don't know if it was like the 1700s, maybe a little bit later. It was a little bit later. I want to say early 1800s. I don't actually know the date. Until not that long ago, people used to think of heat as a fluid that was bottled up inside of bodies, right? And then when heat was dissipated, the fluid, the heat particles, the little bowling ball things, the magic bowling balls, sounds familiar, was transferred to the next one, to the next body. This was mathematically great. We opened up this course talking a lot about how you can have a really good mathematical description for a phenomenon and be completely wrong about how it actually goes down, right? The Ptolemaic versus the Copernican solar system. Turns out that fluids are one of those things that consistently throw us for a loop like this. Heat, it turns out, you can write fluid flow equations, diffusion of fluids. You can write those equations for treating heat like a fluid, and they work out perfectly, actually. You can model heat as the flow of a fluid perfectly with complete accuracy. All your experiments will check out, and it'll be fine. The problem is, it's not true. How did they figure out it wasn't true? Does anybody know the story? There's actually this dude later named Count Rumford, which is a heck of a name. I don't think he was a count at the time. He was some sort of bureaucrat working in the army, I think in Prussia, somewhere in Prussia, during the Prussian Empire. And he was overseeing cannon construction. And the way that they would make cannons was they would have these huge drill bits, and they would ream out the inside of these big iron tubes, or these big iron poles, I guess, right? So you kind of drill out the center of the cannon, right? And Rumford noticed that, like, when they were doing this drilling, the cannons would get super hot, actually, as they did this. And I think in his mind, he started really he started really thinking about the concept of friction a little bit closer. And he also realized that what you would do to cool it down is you would take the cannon after you drill on it a bunch, but if you drill on it too much, it'll get too hot, it'll break the drill bit, so that's not good. So you have to periodically dunk it in this, bucket of water, basically, right, to cool it down. The problem was, when you dunked it in the bucket of water, it would evaporate the water. And he realized that as long as he kept drilling the same piece over and over again, as long as he supplied friction to it, he could generate unending quantities of heat to evaporate this water. He basically started crunching the numbers and realized that the cannon must contain an inexhaustible supply of this magic heat fluid stuff. There was no way for this thing to keep getting more heat particles inside of it. So, we've been fooled before into thinking that action, which is really the motion of particles, in this case, the motion of molecules is how we understand heat now. We've been fooled into thinking that it's the flow of little magical particles in the past. There's a really tragic piece of this puzzle too, because the guy who gave us, he worked with some other people, but the guy who basically gave us the idea that heat is the vibration of molecules and atoms, that dude was so distraught by the way that things were going for him that nobody would listen to his idea, that he ended up actually hanging himself. This is Ludwig Boltzmann, who's a very famous statistical scientist. But he basically came up with this idea that heat wasn't the flow of these magic particles, and nobody liked that idea. So, there's a lot of drama behind the scenes, and there's every reason to believe that we can be fooled by the mathematics sometimes into thinking that we have everything zipped up, and we're completely wrong about it. And I have a feeling that the electron bowling ball is the next version of that to go. Yeah,
The other question I had was just about photons.
another little magic bowling ball too. Yeah.
Yeah. So my question was, if light is not just one thing emitting it and then it goes somewhere, but it's a communication between two particles,
2 atoms. Yeah.
two atoms, then does that mean that photons, like how does the existence of photons play into that? Do they just not exist? Is there not a need for them because it's just a communication then between two?
It's a really good question. There's a so we have to examine why people think that there's photons in the first place. Why is light quantized is another way to think about it. That's a big story. I do want to tell it, but I want to make sure that we've zipped down all of these other aspects. I have some slides prepared to discuss that. Uh, any other thoughts before we move on? That is kind of where I want to go next with it, but I want to make sure that everything we've talked about so far makes some sense at least. What do you guys, before you came in here today, like, how did you think about light? Do you ever think about light? What did you think? Yeah, Ezra.
Um, I always kind of think of light as kind of like our interpretation of the world, kind of. I mean, like there is some like physical phenomenon going on or whatever that I don't fully understand, but what we're seeing out of our eyes is something that our brain is using to interpret the world around us.
It's like a map that we construct.
Yeah.
Using.
From the intake of.
I think that's just accurate for sure.
I haven't like.
I mean, there's so much. To your points, there's so much light in this room that you're not seeing right now. It is just unbelievable. Like there are everything on that electromagnetic spectrum is happening in this room right now. Now, some of the things are happening rather infrequently. Like there aren't that many X-rays bouncing around in here right now, because if there were, we would our skin would melt off and we wouldn't be doing too well. But there are long wavelength radio waves bouncing around in this room. There's stuff coming from outer space, from quasars on the other side of the universe. Like there's all sorts of electromagnetic radiation in this room, and our eyes are only tuned to a tiny little narrow region of it, which we call the visible spectrum, right? That's pretty wild. So you're absolutely right that in some sense, our experience with light is a product of the way our brains and our eyes are organized. Yeah.
So it's definitely like a sight thing, because if you think about people who have like lower like graded vision, like like 10 out of 20 or whatever, and like there's people who are blind, they have like other height sensitivities, and you can feel it. So you can feel the sunlight, and you can feel like the waves coming from the lights. Because I mean I've like sensitive like senses, whatever.
Yeah.
Sometimes I can just feel the light.
Interesting. I believe you. Yeah, that's crazy. Yeah. I mean, another thing that's worth pointing out is that what's up with this visible range? Like, why do we see between, I don't know, whatever it is, like 500 nanometers and 800 nanometers or something like that? Yeah.
Because we only got 3 little light cones.
Why do we evolve those ones? Let's assume the theory of evolution here for a second. Why would we have adapted to that?
Probably because it was just enough for us to comprehend our environment.
But why didn't we see in like infrared or?
Because we didn't need to. We only kept evolved as much as we needed, probably. That's fine.
I have a preloaded answer to this question that I'm looking for. Yeah.
I mean, I got it somewhere in certain, but I think it's interesting. I'm pretty sure we can see more shades of green because of agriculture.
Oh.
That one actually supports the field.
Oh, you're getting close to my answer now. Why are the plants green? Why aren't the plants, I don't know, X-ray colored or ultraviolet colored? Some of them do have some ultraviolet coloring, actually.
I think the dark.
Why aren't they radio wave colored?
I think the darker colors are because they'd actually like burn up in the light. Like if there were black planets, they would, in some regions of the world, they would just burn up people.
So the fact that they're green actually means they're reflecting green, which means they're absorbing primarily red and blue, right? And other, let's say, other wavelengths too, right? They're rejecting the green color. I don't know. I'm getting closer. Why do we? Why have our eyes adopted this particular color spectrum that we're all most of us are seeing right now, unless some of us are colorblind? Yeah.
Probably because the colors that are absorbed by in our atmosphere absorbs everything other than blue, I believe. Blue. And then
It is, in some sense, the atmosphere is playing a part. But where does the light come from? Where does all the light come from? And what's the sun's peak spectrum colors? These ones. This is the peak wavelength output of the sun, or the colors that you're seeing in the room right now. So the sun is white, but if we stick a prism up, we're going to see it split into the colors of this room pretty easily. That's because this is the sun's main color output. Its spectrum covers our visible range really nicely. There's also this incredible coincidence too, which I just absolutely love, which is that the atmosphere that we have is rejecting most of the light that comes from outer space, including most of the light that comes from the sun. Right? We don't want to get hit with gamma rays and X-rays and stuff like that. And even UV is pretty sketchy. Sometimes it can rip your DNA apart, right? But there's this really nice window in the absorption of the atmosphere where it doesn't absorb visible light. It's totally nuts. And there's another little window in the radio spectrum area too. So for some, fortunate reason, most of the dangerous light that would mess our bodies up gets screened out by the atmosphere, gets absorbed, let's say. It's not relayed with high fidelity onward, right? Those atoms, they get excited, but they don't transmit the light on, let's say. But the visible stuff, it gets transmitted on flawlessly. So we get visible light down here bouncing around. It moves around the atmosphere, no problem. I can see you guys because the atmosphere isn't interacting terribly destructively with these wavelengths. There is some. It is not perfectly lossless, but there is a little bit of that. Cool. Thoughts? Questions? Yeah.
I would like to point out to people that magenta doesn't exist. Our brain made it up.
Oh, I have a rebuttal to that. Look up the Gothian spectrum. Look it up. All right, we'll get back to the Gothian spectrum. The chair of the chemistry department was in here one day, and she was teaching. She was talking to some students and said just the same thing. And I pointed out the Gothian spectrum, and then every time we saw her in the hall afterwards, we would be talking about the Gothian spectrum, which is actually a set of shadows. If you put a prism,
How do I spell that?
Goethean, Gothian spectrum. I'll talk about it in a second. Yeah, go ahead,
I
Isaac.
guess this is kind of more of just like a response to Dante, but like, just even if our mind did make it up, wouldn't that make it real? Because everything we're seeing it in a certain way, and somebody else that has a different perception of light would be seeing it in a different way. So just because, like,
I think what he was trying to say is it if you take a prism and you split the light from the sun, let's say, from a white light, you wouldn't get magenta, which is true, But what's really freaking crazy is if instead of splitting a beam of light with a prism, what if I split a shadow? So I put a stick in the path of light and it makes a shadow, and I split that shadow. There was this philosopher named Goethe who did a bunch of experiments with this, and what he found, and for whatever reason, I have one of these that shows up every afternoon in my house too, because there's some sort of like stained glass that just splits the light just right across something coming through a window. But it creates a very different spectrum than Newton's spectrum. Newton's spectrum is just the rainbow. It's the one that we see in the sky when the when the water acts as a prism and splits the light. The Gothian spectrum is different though. It actually creates this magenta and this kind of purplish, let's see, what is it? It's blue, yellow, and magenta, I believe, is what it creates, which is really bizarre. It's completely untouched by modern optics textbooks, from what I can understand. It's just kind of a weird curiosity of the thing. But why in the world would a shadow split? That's just like a completely bonkers idea. I think that the reason that the shadow splits is because all of these atoms are engaged in light all of the time. Sometimes they're frustrated. Like we can take this model that we've built out and go back to the interference thing, right? So you have two slits. You have these. You have two slits. Let's say, yeah, we could just do one slit, but let's do two. It happens with one too. But you have light coming in here, and you have light coming in here, and these waves of light, they kind of add up and cancel in weird ways, such that when they hit the screen on the back of the wall, you get places that are full of light, dark regions separated by light regions, separated by dark light, and you get that on both sides, right? So you get these kind of what we call a fringe, a bifringence or an interference pattern, right? So what's going on with that? Why are these atoms back here getting, why is darkness spreading just like lightness is spreading? It's very, very strange.
The lack of light.
I don't think that it can just be attributed to the lack of light reaching it, right? Because these waves are still reaching.
Just that they're reaching it, but they're bouncing, right? If you look at waves, when you have two different sources of waves, and the waves are water, right? And then they hit each other, the energy of those two gets lowered as they hit each other. And the spaces between the waves grows.
So can you apply that understanding to the model of light that I just built out, being that the wave is not a displacement of anything, it's the impulse of positive versus negative charge on the surface of the atoms at either end?
Maybe. I'm not.
Well, no. Try to apply that same logic to it. So if you apply that same logic, what you're saying is that the dark regions, this is a terrible drawing, I'm sorry. In the light regions, they're both getting told, let's say, to oscillate in the positive direction at the same time. But in the dark regions, they're getting a signal that says oscillate positive, and they're getting an equal signal that says oscillate negative. That's really confusing to an atom because it's getting driven in both directions at the same time. So nothing happens, right? Now that doesn't mean that it's not receiving light, though, you see? It just means it's receiving countermanding signals of light. So it's being told by its neighbors just purely by virtue of the geometry, right? So like it's getting some direct light, straight line, right? But off of the slit, there's a little bit of this light that's bouncing off the slit here, and it takes a little bit longer to get to the back screen, right? And by taking a little bit longer, its phase gets off a little bit. When it's supposed to be, normally if it's supposed to be telling it to turn positive, now its phase is lagging a little bit behind and it's telling it to turn negative, and they interfere. Maybe they interfere constructively, maybe they interfere destructively. But you start to see a picture of light happening all over the place all the time, but the evidence of light only amounting to what the atoms are capable of demonstrating, right? So the atoms might be getting two signals that countermand one another at any given place, and it could just be explained simply by the travel distance which is required in these sorts of slit interference examples. You got light that's direct, you got indirect light, and they can interfere because they get out of phase with one another. It's a little high level, but I hope that makes a little bit more sense.
That makes a lot of sense, actually.
So
that it would appear, so it has a similar effect to like water, but by a different means.
yeah, it's not.
Effect is we observe is similar.
Right. So it's not so much the displacement of units in this wave, so much as we are talking about the time-dependent change in the charge of the atoms at either end, right? In an antenna, it takes a while for the whole antenna to get positively charged and then to get negatively charged. That's a wave of light is what's being emitted. What's happening to those atoms is being transmitted physically. They're pressuring their neighbors in such a way at their outer surfaces to do the same thing. But there's some time that requires. So we obviously can't finish this whole picture today, but when we talk about the Gaussian spectrum, these colors that come out of shadow, what that says to me is that those light signals are still happening in the darkness. They're just getting interfered out of existence is what's happening. So those atoms are still sort of tugging and pulling on each other and doing the light dance with one another. And if the light dance isn't clear to you yet, we're going to make that more clear as we get deeper into this. But even in the darkness, there might be electromagnetic radiation, but it might simply be that the phase relationship between all of those signals is incompatible with seeing something at the other end, with actually measuring light having been there at all. That's the really tricky, magical part about light that I think hides a lot of the mysteries in it.
It was just
One last one, yeah.
the only last thing I'll say is your brain, if you ever wonder why complementary colors are a thing in your brain, it's because anytime you're seeing a color, your brain is immediately processing the opposite of it, what it perceives. So every time you see cyan, your brain is also thinking yellow.
It is
So if
true.
it shifts to white, you will see yellow.
It is true.
If you see, black, and it shifts, you'll see white.
Yeah, perception is a whole other layer of this, but I don't think it's insignificant because a lot of times in physics, what we'll do is we'll take a perception, not necessarily a human perception, but what our measurement device does, our screen or our detector or our electron clicker or whatever, and that perception gets rendered as a phenomenon, whereas the reality is that there's some actual readout that's happening. And we have to think about what's really happening. This is what I'm trying to get at with the shadows versus the light. It doesn't necessarily mean that there's nothing happening amongst all of those atoms in the electromagnetic radiation world. It just means that they aren't productive. They're not exciting the screen to make a signal that we can observe. Sort of like all of the bizarre stuff that happens in your brain too. Doesn't mean that it's actually what you think it is all the time. All right, this is heavy, this is deep. We'll pick up here, we'll review, and we will keep going. And we're going to talk about the photon eventually and all of that. So it's important, guys, hang in there. We can't make sense of telescopes without understanding light. So that's just the way the cookie crumbles. Have a good week.